like California history. Like there's its own individual history class.
Well, that's fair because it's like large tracts of land, and so
Sure.
in analogous terms, each state is a country in Europe.
Yeah, like for instance, you don't learn like French history, do you?
Yeah.
Oh, you do? Oh.
All history.
He just says all history. Wow.
Like
You know-
literally all history.
It's just all the histories. I actually had
In
interesting
primary
thing-
school, it starts with British. Sorry.
No, you good. In primary school, it starts with what?
In primary school, we start with British history, obviously. You know, the Civil War.
Wait, Civil War?
Civil
England
War,
had a
Roses.
The British had a civil war?
Yeah, the parliamentarians against the long. I can't remember now. The parliamentarians against the
Longshanks.
royalists. Yeah.
Okay. What year was that in,
Um,
dude? What? I didn't know the Brits had like a civil war. I guess everyone has a civil war eventually.
After we lost the 13 colonies, so
Ah.
because that's when Parliament went, no, we need the power, not the king. And
No. They're like, y'all messed up. Like, how'd
Basically,
you
we
lose
learned
the
from-
U.S.? How'd you lose the U.S.?
we learned from our mistakes, yeah.
Yeah.
But yeah, by the time you reach sort of the middle of secondary school, so year 9, you start to do French, German, Italian, European history generally, US history, Australian history. Yeah, it's all of it.
Aussie history. That's gonna be a fun one. That's not a knife. This is a knife. Someone in
That's
the
a
chat
spoon.
here. Hendrik Bussy is saying, for me as a German, I can confirm that our schools, we got German history at least 3 or 4 times in school. Twice in history, once in religion, and once in a German language class. That's pretty cool. We got a lot of German history.
The Germans, they get such a bad rap.
Yeah. Yeah, they do get a pretty decent bad rap. At least definitely recently. I was helping a student with their history assignment yesterday, and this dude's like, he asked me, he says, "Hey man, like, when the fuck did you ever use history? You know, like, why am I learning history? This is really dumb. Like, did you ever use history in your day-to-day life and stuff? Like, why am I taking history?" And I tell him, like, well, history is important for recognizing patterns. Like, does it matter that I remember exactly, like, which civil rights bill or which, I don't know, fucking court decision, like, established segregation or something? No, it's not. But it's the pattern recognition of how things in the world, like, keep repeating itself. I think that's, like, an important skill to learn. I mean, why would you say, like, history is important, Sensation?
History is important because people do repeat it.
Yeah.
I mean, it's the whole adage, you know, those who forget history are doomed to repeat it, but it's happening now in this country. Stuff that people fought and died for, and it's like, oh no, you're not allowed to do that anymore.
Yeah, no. Back to square one. Yeah, it's gonna be I think we do live during a very wild. You know, I actually used to be mad about it as a kid in like elementary school. This is before like 9/11 happened. I used to be upset that nothing interesting was happening in the United States or in the world. I was like mad that we weren't at war. Like, it's really like dumb looking back now, but at the time I was like, man, my timeline is the most boring timeline ever. We're not in any wars. We're not doing anything crazy. Life is chill. Like, this sucks. Like, we should be doing something. And are we doing something these days?
I know that's the joke. I mean, things are probably worse now than they've ever been.
Yeah, I agree. Yeah.
It's kind of interesting. You watch old sci-fi shows from like the 90s. Well, not that old for me, but generally.
Sure.
So they would just use racial epithets in the open. Because it didn't mean anything anymore. And then you get sort of post 2000, and it's like, oh, you can't say that. That's really, really bad to say that. It's bad.
Oh, I
Just
see all
never
the
say that.
censorship.
And then all of a sudden, it's all right. We can use these words to attack people now, can't we?
Yeah, because now
bad.
you've given some violence to them, right? By banning them and saying that like these are not allowed. Now you've given some sort of like force behind them. Yeah.
Well, because before it was just a matter of statement. It's like, you know, please don't use that term with me. Why not? Because It's like, don't call me a spongehead or whatever the fuck it was.
Spongehead?
Oh no!
What the fuck's a spongehead?
I can't remember it.
What's up, Amelia?
This was like the 90s, so it's like, you can't say that to me. It's in the similar vein as kike and wop and stuff like that. It's
yeah,
like,
all the racial ones. Yeah.
It was just a statement of fact, and it was like, it kind of washed over you, and it was like, oh well, that's what our parents used to say. We don't say stuff like that, and racism was gone.
Sure. I think maybe probably the connectedness of all the internet and stuff just allowed, I think, these echo chambers to form where now people with like extreme ideas and stuff get to, just find other extreme people like themselves. And then that starts breeding like these weird like cultures around like actual hate. And then we have to come up with like these safeguards that, again, I don't think really apply to, I think most people are not actually racist. I think we're pretty chill people, but we have to like create these things to like try to insulate the basically like the 4chan like please don't come out to the real world.
Because that's slightly different as well, though, because that was people using racial epithets to annoy people.
Yes.
Not necessarily to be racist, just to irritate.
Yeah, it was just to bother people. We call it rage baiting, right? Yeah. See, Hendrik says, I am politically active, and knowing history helps you in a matter of debating on certain topics and knowing certain structures, or better realizing them forming in different governments and Congress. Yes, I agree, Hendrik. Yeah, I think it's always good to be informed. I think just knowledge in general is great. Just like, I think if more people knew shit, we'd have less problems in the world. It'd be great. Amelia, welcome. Amelia's from our UCLA class. Welcome. This is technically my office hours as well for the UCLA students. So they're coming in from like physics, wave equation stuff, and hearing me and Sensation talking about the current geopolitical climate of the world.
Talking shit.
Yeah, that's good. No, it's good. I like to just open it up with things. Slayer says, isn't that because you're biased American media though? Yeah. All media these days is like really fucked anyways. It's almost impossible to get a neutral view on things. And at this point, I can't even believe any of the videos coming out because all this AI generated video is getting too good. It's like scary good at this point. I don't know what's real anymore. Yeah.
See, that's only a problem if you're looking at it on a screen this big.
Sure. Oh, I see. Yeah, yes. So if you're, yeah, I see.
If you're looking at a real size screen, you can tell it instantly.
Yeah, that you can see the things that are off in it and whatnot. Yeah. Slayer says, for Sensation Black, I was talking about this with some peeps today. Revere Clement Attlee. Who's that? Was he UK Prime Minister, apparently?
Yeah.
For his
post-Second World War Prime Minister.
Yeah, for his domestic policy, but his foreign policy decisions were pretty bad, especially his Rush decolonization agenda. We just don't see it because we only look at him for his domestic policy triumphs. Oh, yeah, I see. Yeah. We only remember the good parts.
Arguments about this in secondary school.
Yeah, about like whether he's a good guy or not.
Because basically decolonization was the worst thing that could ever happen to the places we colonized because we were there for so long. They were British essentially by the end, and so when we just kind of said, fuck it, you can have the countries back.
But then there's a power vacuum. Exactly, yeah. It's like they've been spoon-fed on, I don't know, a diet of like something, and then like you just removed it automatically. Just like, now you can't eat cheese anymore.
Yeah, because India is probably the biggest one. It was never a solid nation for hundreds and hundreds of years before we even turned on. Which eventually led to the British Raj around Queen Victoria's reign. And then it was ours for hundreds and hundreds of years from that point on. So.
And then we were like, all right, peace. We gave you like trains and shit. Try to figure it out.
Yeah. We gave you parliamentary democracy and trains. We're out.
We're out. Peace. All right, let's see. Amelia's got a good question. It says, I was wondering if you could go over how wave speed varies with tension again. I have the final occasion written down, but I got kind of lost in the sauce when you were explaining the mechanics of it. Yes. Okay. Yeah, let's do that. Let's do some of that. And then, Hendrik, feel free to like drop stuff in the chat. I'll get to it. But let me do some physics real quick for people. All right, let's start the stream. All right, welcome everyone to Office Hours. My name's Dr. Gold, Sex Education. Stream helps you with math, homework, science homework.
Oh, yeah.
All sorts of fun stuff. We also do discuss geopolitical things. You know what I need to bring back? I need to bring back the Golden Hour podcast. I need to bring that back on Fridays. Just like talking shit about stuff. That was always fun. Maybe I will. Well, this Friday's July 4th, so I can't really do that, but maybe next week. Because we could have a grand old time, Sensation, just like talking about like how screwed up the world is.
A million things to talk about, not enough time to talk about it.
Exactly.
And geopolitics is only one of those things.
Yeah, it's only one of the small facets of things. Let me see. Amelia's asking about wave speed with tension. Yeah, this derivation is kind of screwed up. I remember this one.
Wave speed and tension. Waves to a solid object.
Yeah, wave speed and tension. Yeah, that's actually really cool. Let me explain this. It is pretty cool. So, all right, because I want to go over this a little bit slower. Yeah.
Oh my god, I'm stupid. Wait.
What's up?
Waves. There's two types of waves.
Two types of waves.
One's the compression wave, and the other one's a sine wave. And
Good.
I can't remember what they're properly called now.
Longitudinal. Compressional is like longitudinal. That's the one that does like this. And then transverse is
transverse waves.
He got it. Amelia says, is this like combined education, YouTuber, office hour? If so, that's sick. I vibe with that. Yeah, so before I was even teaching this class, Amelia, I was already doing this like 3 times a week where we just, it's an open office hours where people ask whatever questions, like anything, math, science, I don't care, even like some history questions. And then because it's the summer, not a lot of people really need help with their math or science homework because they're not really taking classes, so it kind of dies down. So I was like, oh, let me just like throw my UCLA class on it because they'll at least give me a lot of like good things to go over. And so yeah, you vibe with it though. That's cool. Yeah, it's like a chill, laid back setting, and the nice thing is that other people learn like while you ask questions. Mad respect for you. You're lit. Oh, I like that. Thank you, Amelia. I appreciate that.
Me sitting there trying to throw up gang signs.
Gang signs. We're just lit. This is the physics. Yo. This is the physics gang sign. It's the QV V cross B, dude. E cross B.
Oh yeah.
Yeah.
Oh, you don't like the other, what is it
the right hand rule versus left hand rule? Which one? I don't like the curl one. I don't like this. I don't like this. I think this one's garbage. I like this.
Is it the left hand rule you don't like?
Well, the left hand rule is if the particles are, I think, negative. Yeah, it depends on whether your particle is like positive or negative. This is like, well, I know it looks like my left hand versus my right hand, but yeah. Hendrik says mainly physics or STEM. It's honestly a discussion about anything, but I give priority to people who are asking specific physics STEM questions, especially physics right now because it's technically my office hours for UCLA. So I just like, I don't know. I know some people like do office hours and no one shows up, and then you're just like sitting there like with, I don't know, your hands up. You're like, what am I supposed to do? So it helps to have an audience to ask other things too. But okay. So yeah, let's talk about wave speed under tension. That's pretty cool. So if you had, for instance, a wave, like not a wave, sorry. Let's talk first about like a piece of rope. Okay. And this rope was tight, right? It was taut. That would have a force of tension inside of it. And what we learn about in physics is that the force of tension acts in opposite directions from like wherever you are. So if you, for instance, had like 2 boxes here and they were connected by a rope and there was some tension in here, this thing would feel a force this way from the tension, and then this box would feel a force this way from the tension. So tension pulls on the opposite ends of things. If we have a section of rope here, we could think about a small piece of that rope having some mass, okay? And what we learn earlier is there's this thing called mu, which is linear mass density.
Mutorant.
Yeah, mutorant. Yeah. Mutorant was the best. We called it utorant though. That's funny. We never called it mutorant.
I did. No, I don't know why.
Yeah, no. You're right. It is supposed to be called mutorant, but I remember calling it utorant at the time. Because
me too, yeah.
Well, I mean, I was in high school. I didn't really know what this was. This is kind of like a college thing when you start getting to the Greek letters. But this is a density, and let's remember that like density in the traditional sense is like mass over volume. So linear mass density, mu, is going to be the mass over the length. Here, this is like a 3D density. And then this is like a 1D density, which means we're only looking at like mass and stuff in like one dimension versus like a 3D shape of it. So if mu, linear mass density, is mass over length, then that tells me that mass is equal to mu times length. Okay, if I just like move this over here. And if we're looking at a piece of rope here, that means this little chunk of mass, delta M, is equal to the linear mass density, mu, times the width of this chunk of mass, which would be delta X. So this is where we're going to get that. Okay, cool. So this little bit of mass, delta M, is equal to mu delta X. Okay. Now, and then there's a tension force on this mass. So you have the tension from the rope here pulling the mass to the left, and you have the tension from the rope here pulling the mass on the right. Think about it like there's just like a box here, and there's rope attached to each side. Tension will pull in opposite directions. Devil says, any tips for the guy that is pulling his fourth all-nighter in 7 days learning mechanics because this one test is way too hard? Oh, man. I don't know if, like, pulling all-nighters is the way to, like, learn things.
The brain is a muscle. It needs rest.
It needs rest. Exactly, yes. Your brain needs rest, yeah. All-nighters are a temporary fix and only really work if you're just doing, like, memorization classes. Like, things like, I don't know, like, biology or, like, history. If you just have to memorize facts, then yes, pulling all-nighters might work. But if you have to, like, learn processes and then apply them in different ways, such as mechanics and physics, you're going to have a bad time trying to just cram that. It doesn't really work.
If you go to the gym and you max out your weight pushes,
yes,
and you just keep doing it the next day and the next day and the next day, eventually you'll start
muscle
harming your muscles
fatigue
irrevocably.
Yes, you'll have a bad time.
You can damage your muscles forever.
Yeah, and yeah, going on 4 all-nighters, yeah, you'll start like losing like some cognitive function. So maybe I would say take a nap, dog. And if stuff is way too hard, like ask someone such as us to try to explain it to you so it makes more sense in like an easier way. Don't struggle too much on your own.
And water, not coffee.
And water, not coffee. I love coffee though. I love a good Java.
That's what I'm drinking.
I left my coffee in the next room. I'll get it later. Okay. So Amelia, let's continue on. Now let's say that this piece of rope, right, is plucked, okay, such that it's going to oscillate to the left and to the right, or it's going to oscillate. Let me see, make sure I get this right. Oscillates perpendicular to the wave motion. Okay, good. Yeah. So this thing is going to oscillate up and down as such, but the wave is eventually like moving in that direction.
Just out of curiosity, are there no transverse properties in a rope as well, like that?
Yeah, no. This is you have a rope that's tense and if you like whip it this way, what happens is the rope oscillates in this direction, up and down, but the wave pulse moves left to right.
Uh-huh.
And this is why it's called transverse, is because what do we call it? The amplitude is perpendicular to the propagation. So that's just a fancy term for like the wave moves up and down, which is 90 degrees to it propagating, like it traveling to the left and right. Yeah. But wait, I want to make sure this F1 and F2 makes sense to me. If you pluck... What's up, Equity? Good to see you, dude. And good to see you, M.A. Diong. You have issues with machine design. Ooh, interesting. Well, you can submit a screenshot using the link down there. I'll get to it after this. Just make sure this is fine. Okay.
Remember, screenshots plus.
Screenshots plus. And the positive and negative x direction is constant. Cool. Love that. The net force of the string is the sum of the tension force and restoring force. The x component of the force of the tensions cancel, so the net force is equal to the magnitude of the x component of the force equal. Yeah. Okay. Oh, I think I see what's happening. Okay. Right, okay. Okay. If this thing is being plucked, okay, and it's moving, right? Then there's a force, right, moving this section down, and there's a force moving this section up, and that's going to be F1 and F2. Okay. FT, the tension in the string has to be the same. They don't draw this to scale. They really should, right? Is this not to scale? No, it's not. Oh my god. Who created this diagram? That's terrible. Yeah.
It's not a thing though. You always assume that it's not to scale.
I guess you do, but like that's really bad for them to do that. Okay. Right, okay. There's tension in the rope. That pulls to the left and to the right. That has to be equal. But then there's also up and down forces which are causing this thing again to oscillate up and down, right? The amplitude, which is like the movement of the string, is perpendicular to like how the wave is propagating. So what we can then do here is think about what the slopes are. Okay, I see. Okay. So, if we consider this point right here, okay, and I want to talk about what's happening here, right? The slope of this would be equal to, this would be dy dx at, we would say, position x2. Okay? Like, that's the slope of that. And the slope of that is the same thing as the opposite over adjacent of f1 over, f2 over ft. One sec. The tangent of theta. Okay. I do not like this derivation, actually. And F1, 2t is equal to the slope of the string at F2. Yeah, this, where are they getting this one? One sec. Oh, okay. Okay, no, I think I get this. Yeah, okay. I don't know why they make the tangent argument. We don't really need the tangent argument here. Yeah, okay. The slope of a function, right, is change in y over change in x. And in that case, that's going to be the y force, which is going to be F2 over the x force, which is Ft. Okay? So the derivative of this, which is the slope of this, is the same thing as rise over run, right? Right, change in y over change in x. And that's of the forces. Okay, so that's how we get that. Then if we look at here, which let's call this instantaneous slope dy dx at x1, okay? That's the negative of this. Like, this over this is a negative slope, because let me show you. That points in this direction, right? So this is equal to negative f1 over ft. Right. Because I need the slope here to be negative. Okay. Okay. I got it. I think I got it. Negative 1 over ft is dy dx1. Okay. All right. So then we try to figure out what the net force is on this section of mass, right? This little piece of mass, which is equal to mu delta x. And what we see is that the tension forces cancel out. Okay. So the only thing I really care about is F1 versus F2. And what I have is, so, okay, that's going to be F1 plus F2. But from here, we can say that, okay, cool. So F1 is equal to negative Ft dy dx at x1. And F2 is equal to positive Ft times dy dx at x2. Okay, 1 sec, Amelia. Let me make sure this makes sense to you, right? Because it's important that we get this, right? So F2 is Ft dy dx at this position, and then F1 is negative because it points down, and it's Ft dy dx at x1. In this case, Ft is a positive number all the time. It's just like a magnitude. I don't know why they start talking about tangent and stuff. They really shouldn't have done that in this textbook. That confused me, dude. Like, look what they say here in the textbook. They say, to obtain the y components of the force, note that tangent of theta 1 is negative f1 over ft. Tangent of theta 2 is that. The tangent of theta is equal to the slope of a function at a point? I mean, kind of. I don't know. This to me is like confusing. I wouldn't bring tangent into here, which is equal to the partial derivative of y with respect to x. You can just say that the derivative of a function is the slope, and then that the slope is the change in y over the change in x. Good. If f2 is pointing up, then why would it be the slope times the tension? Okay. So f2 is pointing up. Okay. So if I want to look at the slope here at x2, the slope at x2, right? That's the rise over the run, which that rise over run is equal to this rise force, which is F2, divided by this run force, which is Ft, right? You can think of this is like Fy over Fx. Like, we think about that, I guess the curvature of this wave has to be due to the forces that are kind of deforming it. And the ratio of those forces, the y over x, also will be the slope of, like, the shape of that thing directly here. Right? Okay. And so F2 is pointing up. Okay. So this is, right, delta y over delta x, which is ft, okay? And that's equal to the slope. So now if I take this and just multiply it on this side, that gets me that f2 is equal to ft times my partial derivative at x2. And then by the same token here, right? In this case, the slope is equal to negative f1 over ft. Because dy dx here, that'll pull out a positive number. The slope will be positive here. Oh, you got it? Nice. Is my statement not working? Yeah. Yeah. So slope is... No, you're totally cool. It's alright if you're 8 seconds behind. Yeah. I'll wait. It's okay. Totally good. But yeah, even for myself, I had to kind of like... this kind of bugged me out here. I was like, wait, what's going on? But like, yeah, this slope is equal to negative f1 over ft. Because f1 is like down. And so then when you move it over, you get f1 is a negative number, which it should be. F1 should point down. This is another thing in physics that math people get super horrified with is we tend to just like kind of ignore minus signs and just place them wherever it makes sense, like visually. You know, the classic example of this is if you have, for instance, let's say something like pulling up on a rope. Let's say like, you know, you're pulling up and then you have the force of gravity pulling down here, right? When we say like sum of forces, right? That's technically equal to like FP plus FG. But a lot of times what we'll do is we'll be like, oh, but FG is down. It's negative. So instead of saying this, I'm going to say, oh, cool. This is just FP minus FG, where we assume that the magnitudes of these things are always just positive, and that whether there's a minus or a plus in front of it, that denotes the direction. Technically, FG is equal to mg in the negative y hat direction. But I see students get confused all the time with this in mechanics, because they'll say, oh wait, but gravity points down, isn't it negative 9.8? So shouldn't this be m times negative 9.8? And then it's negative. And then, yeah, if you're consistent there and then you add it, then sure, the negative comes out. But if you plug that into here, then you have another negative, and then it turns it into positive. And so what I always tell students is that, like, acceleration is equal to negative g. But g is always equal to positive 9.8. This is always a positive number. The negative out front here just denotes the direction of it, which in some cases, for instance, if you're running like an Atwood machine, if you're doing one of these things, okay, now acceleration due to gravity isn't always negative, because it depends like what direction you say positive acceleration is. Let's say, for instance, this is like 3 kilograms and this is 2 kilograms. Naturally, this whole thing would like rotate this way, right? Like the heavier thing would go down, this thing would come up. In that case, I'm like, okay, cool, positive, negative, positive, negative. Now, when I calculate like force of gravity here, the force of gravity is equal to positive mg, because the force of gravity points in like the overall direction of positive acceleration, because this whole system, when it moves counterclockwise, is positive acceleration. Whereas in this case, this fg is equal to minus mg, because it is pointing opposite to the direction that like the system wants to move. So yeah, I say G is always 9.8, but whether something is positive or negative out front depends on your coordinate system and depends where things are going. In this case, like this thing going down is positive acceleration, and this thing going up is positive acceleration for the whole system. You could also flip it. You could also say that this is negative, this is positive, this is negative, and this is positive. But then these flip. Then this is positive mg, and then this is minus mg. So, I know, yeah, it's a lot, but like, yeah, physics is, with the minus signs, don't get too like invested in, I have to make sure I have the right mathematical minus sign. You just look at the picture and determine what it should be. It's kind of like my best explanation. Math people hate it. When I say that, they get so mad. They're just like, no. You can't just arbitrarily assign minus signs. But I'm like, but yeah, bro. I mean, that's how it works. And I think it'll make the most sense. Like in this case, I know this derivative is going to be positive, but I know F1 needs to be negative, so I can just like put a negative sign in front of there. Because technically looking at this way, this is kind of weird because like F1 is negative and Ft is also negative. So these would cancel, right? And then you would, I guess you would also get you would get a positive slope there. But I'm crying. The cats, yeah, the cats are so good. So I just fucking put the negative here. That's what I tell kids to do. Just do it. Just do it. Do it. Okay. So let's get, now that we've identified minus signs and all that fun stuff, if we wanted to look at the sum of the forces here, right? F1 plus F2. Okay. I'm going to have F1 is negative. It's pointing down. F1's pointing down. So I have negative Ft dy dx at x1 plus F2. F2 points up. That is positive. So I can leave that as positive. And this is going to be plus Ft dy dx at x2. And this needs to equal the mass times acceleration of my chunk here. And in that case, the mass times acceleration is going to be, let's remember, the mass is going to be the mass density delta x. So what the mass density is, how wide in delta x that is, times the acceleration. And the acceleration of this thing is going to be d squared y dt squared. Okay? Because this thing is, this little mass here is accelerating like up or down. Let's remember that acceleration is like the second derivative of position with respect to time, and the direction it's moving is the y direction, so that's the derivative we care about. All right. So then from here, I'm going to pull out an Ft from both of these. And I'm going to get, and I'm going to also switch them, the signs of them, because this is positive, this is negative. So I'm going to get dy dx at x2 minus dy dx at x1. And then we're left with that. And then the last thing I'm going to do, well, not the last thing, cool little thing I'm going to do here is I recognize this stuff all depends on x. And this also has x. This is an example. So you'll learn this in math. But with differential equations, when you have different variables going around, like derivatives with y, derivatives with x, derivatives with t, you want to try to get all those variables in the same place. So in this case, I see a bunch of dx's here. I also want anything with x to be over here. So I'm going to take this and pull it this way. And then this I don't really care about. So I'm just going to pull it over here as well. I want to try to keep everything in one place. So here we got dy dx x2 minus dy dx x1 all over delta x is equal to mu over ft And then that's d squared y dt squared. Okay. So let me stop there. Give like a little 8-second delay thing. But Amelia, you let me know if that's good so far, or if there's any parts of that you want me to explain. We do this in physics where we use like a diagram and pictures and force whatever the fuck to like create these equations. And then at some point we just like turn off our physics brain and we just slam the accelerator on like it's math time. And that's kind of what we're going to do at this point. Is I've kind of figured out the physics of getting to this part of the equation, and now I'm just going to think about it just in terms of math terms, and some cool stuff will pop out.
That's weird.
This makes sense. Thank you. Awesome. Cool. Okay, great. I want okay, I want x2, x1. I want this limit definition of a derivative, but I want it in like a nice form. Okay, whatever. I mean, I guess this kind of works. I'll take this. Is your image not showing? Brick.
That was weird. Why was that not showing before?
Dude, I wonder if it... Well, a Discord does, like, auto-censor shit sometimes. Where, like, it's like whatever's censored, and then I have to click on it to, like, see it. I don't know. They're adding new shit all the time. Okay. So, something... See, I have to click on... I gotta click on this as well. It's the Happy McFindout. I'll continue to click on for you, Sensation. Okay. What I'm going to do, Amelia, next, which is a little trick here, is I'm going to take the limit as delta x goes to 0 of each thing here. So what we're doing is we're considering that instead of looking at like some, you know, finite chunk of mass here, I want to think about like the infinitesimally small like point mass, like what's happening there, like what's happening on like the individual particle level. And the way to do that is to shrink my delta x really, really far down so that I'm just looking at basically where delta x is 0 and we're only looking at one thing. So I'm going to take the limit as delta x approaches 0, okay? And yeah, doing that on this side, that does fuck all because, I mean, there's nothing with x here anyways, so like whatever. So the cool thing here is that this part of the equation right here is the same thing as what you learned in calculus.
That's dope.
The limit definition of a derivative. I know everyone in math like fucking hates this when you learn the limit definition of a derivative, because you just learned the power rule like the next day and you're like, why did we learn this? Like, this thing sucks. But it turns out it's actually useful here. Okay. What this states, right, this limit definition of a derivative, is that if you have 2 points, let's say this is x1, let's say this is x2, and let me make it like kind of like cool. There we go. And I'm trying to figure out, and then here, let's say this right here would be f of x1. And this right here would be f of x2. Okay. If I want to find the derivative at x1, right? If I want to figure out, like, what is f prime at x1, that's equal to y minus y2 minus y1 over x2 minus x1. Right, it's equal to like the slope between x1 and x2, which would be fx2 minus fx1. These are the y values at x2, the y values at x1, divided by x2 minus x1. Okay, and this x2 minus x1 we will sometimes say that, okay, well, this is just the same thing as delta x, right? This is just delta x. And you should see like a pattern here, right? This is the slope between x1 and x2, but the derivative occurs when you have that distance between x2 and x1 going basically to 0. So we say when the limit as delta x goes to 0 of this. Like, for people watching who don't really remember calculus and stuff, it's okay. So what you're doing is you're taking this x2 and you're moving it as close as you can here. Oh, why can't I move this? I should be able to move this. Yeah. Because the closer you move x2 to x1, the more accurately this, it's called the secant line, the line between x1 and x2, predicts the instantaneous slope at x1. Is where that comes from. Yeah. Okay. There. So this is basically the same thing as f of x2, right? X2 is just equal to x1 plus delta x, right? This point here is just this plus this. So this is fx2 minus fx1 all over delta x, which we have the same thing here. But in this case, this is f. Oh, the submit page keeps redirecting? Oh, that's weird. Why is it doing that? Let me check it for you real quick. It shouldn't be. When you hit submit or when you go to the web page? Well, mine works pretty fine. Although it does say our connection is not secure. I probably got to fix the SSL certificate on that. It's so annoying. Yeah. Let me think. I think it's submit dot. Oh, when you try to visit Safari, it doesn't load. Can you try a different browser for me? I think Safari like fucks up. Here's the other thing, Guitar Ninja. If you go to, let me find it for you one sec. Where is my chat? If you go to the main webpage, so if you go to that, you'll see this, which is literally like my fucking Apache server, like index of. And then if you click on this, it'll take you to it. It should. There might be some weird thing with the redirects with Safari. I know this because it was a bug I was dealing with earlier, trying to get SSL certificates for it. I built that whole website myself, just like off of like raw like command line and like a Linux server. And unfortunately, there's just so many weird things for getting certificates to work correctly. But try that, Guitar Ninja, if it works. Okay. Anyways, back to here. So this looks like this, for instance, is f of x2. And then this is f of x1. And so what we're really doing is we're taking the derivative of f, which in this case is the derivative of partial y over partial x. That's what this whole thing becomes. This whole thing becomes the derivative of partial y over partial x. Is equal to the same, right? Mu over ft d squared y dt squared. Here, let me move all this down somewhere else. Running out of space. Need more space. So there you go. That's that. And so now, since I have like the derivative of a derivative, this is the same thing as the second derivative. And so this is all going to turn into the second derivative of y with respect to x squared. Sorry, this was ddx is what it is, sorry. right? Right. df dx, is that over delta x? And then this is equal to mu over ft d squared y dt squared. Okay. And then the reason why this is cool is because it looks exactly like the equation we derived earlier, like the wave equation, the linear wave equation, which was this. You see how we have kind of the same thing? Second derivative with respect to x is equal to some constant out front, right? In front of the second derivative with respect to t. And so from that, now I can say, oh, well, 1 over v squared is equal to mu over ft. You can flip both sides such that you get v squared is equal to ft over mu, and then square root, and you get that v is equal to the square root of ft over mu. And this is your final answer that describes the wave speed on a rope with tension and mass density. Yes, that's the big finale. Anyways, I'll give you some time to respond to that, but let me know, Amelia, if that makes sense, where that comes from. It's quite a lengthy explanation, but I think it is really cool. It's very cool that it comes out to be that. It's very cool that it's self-consistent. Yeah, Amelia says, ooh. Well, make sure the ooh is like a good ooh, not like a bad ooh, you know? Not like a, oh no, the cat's coming out again.
Wait, you should have done the oh no thing.
Oh, where is it?
Oh no.
That one, the oh no one.
No. The monkey one.
Oh,
You gotta get in the hospital.
wait, I gotta go find it. Oh, that one is probably like that. Yes. Where is it?
You gotta get in the hospital.
No, that's, well, where's,
You gotta get.
dude, it's random actually, so there we go. This is it. Oh no.
Oh no.
Oh no.
Oh no. No.
Okay, Amelia says it makes sense. Awesome.
Love that one.
Love it. Nice. Oh. Okay. Cool. That makes more sense to me now. When someone speaks and their voice is recorded, how is it separated from the background noise? Like with a microphone? I mean, usually they're pretty directional is what they are, right?
Yeah, this one is.
Yeah. Depends what type of microphone you have. I mean, these things do definitely pick up background noise. Like, if I start turning my fan on, like, you'll hear the fan. I'm glad, Amelia. Yeah. There is active software that can try to remove background noise using algorithms, and the way they do that is, just in general, if I were to record sound and upload it to a computer, to remove the background noise usually occurs at frequencies that aren't the human voice. So for instance, if there's like a high-pitched ringing from I don't know, like a ceiling fan or something, or some electronics that are on that are buzzing, or maybe it's a low frequency thing, like say you're on the ocean and you're speaking, but there's this like woo, 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 woo. If the frequency of your background noise is different than your voice, you can do what's called like a band pass or a band cut, and you can remove certain frequencies out such that they're no longer in the full signal. That's the way they do it. And then I don't know, AI probably does some really crazy shit these days, but it's kind of like the simple way of doing it. They do it using an FFT actually, which is really cool. I'll explain FFTs later if I have time. FFTs are really cool actually. They're super rad. Okay.
Where it's like totally gnarly.
Totally nah, bro. Okay, let me see. We probably have some submissions from people on the web stuff. Oh, Guitar Ninja, nice. Okay, cool. This is a good question from Guitar Ninja. It's a physics one. You're welcome. You're welcome, Amelia. Peace.
Oh no.
Oh no.
Oh no.
Oh no.
We gotta get you to actually. Oh no. You know, it's the NAUR. It's like.
Oh nar.
Oh nar. Oh nar. It's like oh nar.
No.
Oh man. Okay, let's see. This is a good question from Guitar Ninja. Looks like Guitar Ninja got their thing to upload. Congrats. What is the required velocity to escape the gravitational pull of a planet with a mass of where is it? Where is it? Oh, okay. Mass of 6 times 10 to the 24 kilograms and a radius of that. Ooh, okay. I believe this is where you need your kinetic energy to equal the potential energy of gravity. Yeah. I believe that's how we do this one. This is just a simple mechanics question, I think. Okay, so one thing to know is gravitational potential. Have we done gravitational potential before? In your class? Let me know, Guitar Ninja, if you haven't. Gravitational potential. So, one sec.
Is it like big G1 R1 over
Good.
big G2 over fuck yeah.
Yes.
I was halfway there.
You're right. So we learn gravitational potential energy on the Earth is just equal to mgh. And this is like a simple approximation for things that are on the Earth's surface. And we say that G is equal to 9.8. It turns out that like if you're talking about big fucking things like planets and celestial objects, you have to use a more complete form, which is capital G. And then it's M1, M2 over R. Okay? So this is the potential energy of big objects in space, okay? Where G, I believe, is equal to 6.67 times 10 to the... Ooh, what is it? 10 to the minus 11. M1 is usually like the mass of your planet. So that's going to equal 6 times 10 to the 24. M2 will be equal to the mass of whatever my spaceship. And then R will equal like the distance from center of the planet. Okay. So, in order to escape a planet, you need to have enough kinetic energy to replace the potential energy that is trying to like keep you there. So, you can think of it this way, right? If you are located some distance here, some distance R, let's say the rocket ship starts here, okay? You have potential energy equal to G M1 M2 over R. And then what you need to do, and let's say you're moving at like some initial velocity off, like some V0, that means you're going to have some kinetic energy equal to 1/2 mv squared. And by conservation of energy, right, as let me think about this. As you start to get further away, your potential energy drops. Well, one sec. I gotta think about how like potential energy works because it's opposite now. Because zero potential is here. This is so when we talk about like big gravitational energy, this like way out here at infinity, this is mu g is equal to 0. Versus when we do on Earth's surface, right? We call this mu g is equal to 0. Like we would call on the surface 0, but here it's not. Let me think. But I don't think your potential energy is ever going to actually be 0, right? Because you'd have to be infinitely far away from the planet. I think. Let me do a little bit more research. Because I want this to be like I know what the default equation is. Which is just that kinetic energy equals potential energy. Like the potential energy, like trying to keep you stuck there, has to equal the kinetic energy that you're trying to like lift off with. And then you just end up saying this: 1/2 m2 v squared has to equal g m1 m2 over r. And then you just solve for v is what you do, because the cool thing here is that the m2s cancel. And then you get that, what's this? V squared is equal to 2g m1 over r. So then v, which is the escape velocity, has to equal the square root of 2g m1 over r. Which, this, let's see, where's my calculator? Because we had a bunch of numbers there. So 2 times, yo, what's up, Skeeg? 6.67 e to the, what is that, negative 11 times m1,
Nice.
which is 6. Thanks for the follow, Snowflake on Beauty. No way bro is educating us on physics. Yeah, I am, dog. It's real. It's real, dog. There can be educational shit on Twitch. And then, here, let me divide that by the radius of the Earth. This is for real, dude. It is. What's the radius? Oh, 4 times 10 to the 7th. Okay, and then we gotta square root that. You're struggling? Well, then, yeah, submit a question, dude. I'll help you out, dog. There's a website down there. Here, let me... If you submit a screenshot to that website, I'll see it on the Discord, and then I'll go through it. Okay, cool. What's up, Nigma? So we get V escape is equal to, what is this? 4.473 meters per second. Cool. So that should be answer choice C. Okay. Yeah. I mean, that's how you do it. And sometimes actually in your classes, they just make you like, just figure out what this is. But I'm not exactly happy with that. I don't like memorizing equations. I like trying to derive it from first principles. Let me think of it. Hey, you tutored a student in physics last semester. Nice. What level of physics was it, Enigma? Yes, and there's also the Discord. Ah, okay. Oh, grade 11, so pretty basic stuff like dynamics. Cool. Yeah, no, that's great. That's what I was teaching last quarter for sure. Okay, actually, yeah, I was right here. Okay. So, it comes down to like what the definition of escape is, right? Yes, Equity, I'll go through yours. Thanks. Sorry. Yeah, I was answering some of the physics people. So, escape is really cool here. So, if you get out to infinity, this is considered escape. And if you want to figure out the minimum velocity for you to escape, you want it so that, like, once you've reached infinity, that your kinetic energy is equal to 0. This is, like, the minimum velocity. This is where it's kind of silly because, like, bro, you're never going to get out to infinity. But basically, what it's saying is that you're escaping the Earth's gravitational potential because you always have enough kinetic energy in the tank to beat out the gravitational potential trying to pull you back. So at the beginning, so we could say, like, you know, on the surface, you have potential energy, which is equal to G m1 m2 over r, and you also have kinetic energy, which is equal to 1/2 mv squared. Okay. And then when you escape, we say like at infinity. I see, and the gravitational potential energy is negative. Oh, okay. Where does that come from? Isn't that like F is equal to negative grad U? I support the support, bro. I appreciate it. I do support some support.
And if you would like to try that again in English, please do.
Yeah. Try that again in English.
Yes, you got baby
Or any
voice going.
language, I don't care as long as it's correct.
As long as it's some form of correct English, we'll do it. Yeah.
Well, no, I'm saying in any language, I don't give a shit as long as it's correct.
And as long as Sensation can understand what language it is, which is probably like Japanese or something.
I can understand most languages, to be honest.
That's true. I think F is negative grad.
U. So U is equal to negative F dot dx. The force is negative. And then this is the minus signs that always like bug me. Yes, okay. You have 0 gravitational potential out here. And then it's like the work required to bring it in there is negative work. So you have negative potential. Okay, I think I get this. Okay. Yes. Okay, here gravitational potential energy is 0. Here gravitational potential energy is negative. Aha. And then at a very far distance, when you escape, mu g equals 0, and your kinetic energy is equal to 0. Oh, wow, that is wacko. Crazy. Yeah, this stuff always like kind of like bugs me out. Okay, but just set gravitational potential energy equal to kinetic. What's up, Sensation?
¿Por qué?
¿Por qué? Okay, I do have some screenshots from, I think Equity has one. And then Pervots. Pervots, my... Dude, why are actually none of my images showing without me having to click them? That's interesting.
Streamer mode?
Yeah, maybe. Dude, actually, you know what's funny? It does. It thinks like I'm playing OBS, like just because I'm like streaming my my OBS output to Discord. It thinks like OBS is a game. Anyways,
the game of streaming.
Oh, I lost the game again, dude.
Oh no.
The game 2.0.
The game 2.0. You are now aware that you are now breathing manually. Don't let me forget, dude. All right. Let's see. Where's Equity? Equity. And Snowflake. Let me know when you submit a screenshot. If you can't figure out, or if the website's not working, I feel like it should be working because we got some people. You can always go into Discord, and then there's a channel here called Help Screenshots, and this is where people like submit screenshots for questions they have. So that's another way to do it. Okay. All right, Equity. This is a lot, dude. Like, do you want me to go through all of this, or is there a certain point of it? Point X then passes through its resting position, returns above its resting. This occurs 200 times in 1 second. Okay, some cool information here, Equity. So if something is oscillating at a certain rate, like times per second, that's a frequency, which is going to be equal to 200 hertz. And then they say it's 2 millimeters above and then 2 millimeters below. That tells me my amplitude is equal to 2 times 10 to the minus 3 meters. Okay. So P is equal to 1 over 200. The period, correct. Yeah. We don't use P for period. Please don't do that. Use this capital T. So 1 over 200. Yeah, and that's in seconds. Okay. Determine the possible coordinates for the 5 points F, G, J, K, and P. Okay. Well, I mean, that's pretty easy. So, yeah, if a period is... It's a trig question. Oh, so this isn't even physics. Oh, that's kind of cool. All right. Well, sorry, did we say it starts at the highest? Oh, it starts at its highest position. Okay. So, you know what this coordinate is going to be. This is time equals 0. Let me get a better color. Maybe like bright green. Is that easy to see? No. Orange? No. Oh, red. Red will work. Yeah, red's very easy to work. Okay. So this point right here, so this is going to be, this is the x-axis. This is going to be 0. So this would be 0, comma, 0.002. That's that. I could, but the key thing here, Jeff, is they said at time t equals 0, it starts at its highest position. So, and good to see you, Jeff. You're right. I could do a sine function with a phase shift. I totally could. I'm just going to call it a cosine function. Oh, and actually, no. You're actually right, Jeff. I am going to have to put a fucking phase shift on it. That's annoying. Okay. Correct. Thank you. Thank you, Jeff. Jeff is right. Okay. This is 0.0002. And then this other point here, right? This is going to be a full period away. And a period is 1 over 200, which is, what is that, 0.005? Is that what that is? Why are they using such gross numbers, dude?
Oh, no.
Such gross number. What? Why? Okay, 0.005. Right, okay. So this will be 0.005, comma, 0.002. And then this is going to be the midway point, right? So this is going to be 0.0025, comma, negative 0.002. Yeah, too bad you can't use millimeters and milliseconds. Can I not? Do they really want meters? Yeah, fuck that. Yeah, let's just use millimeters and milliseconds. Let's do it. Let's make life easy for us. Okay. This is 0,2. We're dealing with things in millimeters and milliseconds. Okay. Then this point right here is going to be 0. Sorry, it's going to be 5,2. So sorry, it's milliseconds, comma millimeters. Then this is not so bad, right? Because then this I know is 2.5, comma, negative 2. And then this is halfway in between that and that, which is 4.25, comma 0. And then this point right here is going to be 1.25. Sorry, this is 4.75. Wait. No. 3.75. 3.75, and then this is 1.25, comma 0. There we go. Yes. So this to this is a full 5. So then this to this is half that, 2.5. This to this is half of that, which is then 1.25. Does that make sense, Equity? Is it asking in millimeters? They do the time as as a function of seconds, though. That's annoying. Yeah, so just convert the times by dividing by 1,000. Okay, so then they want to talk about the function. Okay, well, this is easy. The amplitude is 2. So we say h of t is equal to 2 sine, and then this is, it's omega. I always mess this up. I think it's t plus phi plus d, or this is the midpoint. But the midline is 0. Okay, so this is 0. This I screw up. Yeah, there is. So omega is equal to 2 pi over the period. So this is going to be equal to 2 pi over 1 over 200. So that's going to be equal to 400 pi. So we have h of t is equal to 2 sine 400 pi, and then it's t plus the phase shift y equals negative 2. Where? Yeah, I don't think it's 1 over 200. I think it's omega. This is also the same thing as like 2 pi times the frequency. And the frequency is 200, so it should be 400 pi. And then you have to think about like how much it's off by. So it's off by, it's scooted to the left by a quarter of a, by this much time, right? So sine would start here, but I need it to start here, which means this looks like sine, which has been shifted to the left by this amount of time. And that amount of time is 1.25 milliseconds. So Yes, there you go. 400 pi, good. And then I agree with this. This is going to be, yes, 0.00125. Yeah, good. I don't think it should be -2, though, Bob. I think it should be positive. Unless you were shifting it to the right and then it's negative. Yeah. Negative sign looks like this, and in that case, yes, that is a minus phase shift. Remember that minus on transformations for functions shifts things to the right? Positive shifts things to the left? Yes, positive sign goes up instead of down, right. So this is positive sign, Bob. Right, this is positive sign. So I need a positive sign function, right, that was here, and it needs to be shifted to the left. And if it's shifted to the left, that's plus. If it was negative sign, then this looks like a negative sign that's been shifted to the right. And shifting to the right is minus x, or minus phase shift. Do you remember this comes down to like function transformations, right? So if you have f of x is equal to something, let's say it's this, then let me do this. Then f of like x minus h ends up equaling like that. And then f of x plus h looks like that. So this like shifts left. And then this shifts right. Okay, cool. The t-coordinate of g is t1, and the t-coordinate of j is t2. On the interval t1 to t2, which of the following is true? Well, the height is negative, and it's definitely decreasing. Describe the concavity. So that's cool. So if we're looking at the concavity of this looks like what I say is like a happy face, which means it has positive concavity. So this is this way, which is positive. And what that says is like, so the rate of change goes from being like kind of negative to not very negative to being 0. So the rate of change is increasing. It's going from negative to 0. If you're going from negative to 0, you're going up. Even though I know it looks like it's still like pointing down, but the rate of change is changing from negative to 0. That's a positive change. And then from here, right, it starts going more up, more up, and more up. Increasing slope is also an increasing rate of change. So it's increasing. Nice. Does that make sense, Bob? Yeah, nice. Sick. You're welcome, dude. Nice. Man, I feel like that one question just on like deriving the wave, man. Holy shit, this like took me out of it. That was so much math. Okay. I feel like I need a sandwich or something. I haven't eaten. Oh, nice. I got paid. Love that. Love getting paid.
Got to get paid.
Gotta get paid at some point. I don't know. I submit hours for like certain invoices and just never hear back until like weeks later. And then I'm like, oh my God. My rent is due today, please.
Invoices.
Yeah, I do different things, right? I do like some cold consulting work. And actually, like that party I DJ'd over the weekend. I had to send an invoice for as well. I got paid to DJ my friend's like after party at a club. It was actually really cool. One sec, I think I have a funny video of it because there was this hilarious moment when man, where did I think it's on my Instagram. It is on my Instagram. Give me a second here. So I was DJing on the decks, and some girl came up to me and she says like, I love the music. I was like, great. And then she asked me if she could like plug her vape into the decks to charge it. It's like, go watch, I'll show you, dude. It's fucking hilarious, dude. This is me. I have like a pretty decent transition here. And then you'll hear it, like she comes up to me and asks. Dude, she's like, do you have a USB to charge my vape? And I'm like, no. And she's like, I have the cord. Can I just plug it in there? And what she's referring to, I'll show you. It's a CDJ Nexus 3000. What's CDJ? She's referring to the USB port on this thing at the top, which is meant for me to like load my music on. One second, if I can find it. Or nothing wants to load today. Come on. Yeah, there we go. Yeah. So you know what? Technically, it does say 5 volts, 1 amp. Technically, that would charge a vape. I mean, she is right. That's hilarious.
Yeah, but I mean, she sounded like a Valley girl, so you should have just said it's not powered.
I mean, I was concerned that if I plugged a vape, I don't know, these fucking like whatever Chinese cancer death stick machines, like I have no clue how much current that thing's gonna draw. Well, I mean, yours doesn't look as Chinese. I'm talking about these puff bars. Do you guys have these puff bars in like the UK? You know what I'm talking
about? There's many, hundreds of types, thousands even.
These things are absolutely terrible for the environment. Yeah, they're called like geek bars or something. Dude, I fucking hate all this stuff, dude. This stuff is so dumb. There we go. Like do you guys have these?
Yeah.
Dude, some of them have like screens on them now, which is ridiculous because these things are disposable, right? Think about all the fucking e-waste we're creating, dude. That like these things, yeah. Look, dude, some of them have like, they have like video games on them and stuff, dude. Like what?
The disposable ones were banned here.
So interesting enough, the reason why they're disposable here in the U.S. is that there was a law passed that you couldn't sell flavored nicotine things that were reusable. Well, so like the original thing came around because like too many kids were like smoking flavored nicotine, which right, the whole point of these things were to get people off cigarettes. But now they just got kids addicted because you got like fucking flavors like mint berry, jazz, apple, whatever Pop-Tart thing, right? And so they put a law out being like, okay, well, no more flavored nicotine. Like, that's illegal. Unless it's one-time use stuff. Which I'm so confused why this loophole was put in. Because what it ended up doing is just having all of these companies create these, like, one-time use bar things, which are terrible for the environment and, like, e-waste. That's funny that they're banned in the UK. That sounds smart.
Too much e-waste.
Yeah, it's terrible.
So they started selling. Hang on. I can't.
No, I see
They
it.
started selling these separately.
Blue. Yeah, I know this company, Blue. Yeah, I know them. They're one of the OGs.
And then you get one of these. Oh, shit.
And then you have pods. Yeah, no, I see it. Yeah, and you have pods that you're supposed to put on. Yeah, that's originally what like a Juul was. Yeah, that's originally what this was. Juuls were like, you had a battery charger thing and you had a little pod and you put the pod on. I was like, okay. The issue again is that like too many kids in schools were smoking these, so they banned them. But then for whatever reason, there's a loophole that if they're disposable, they're not banned. Which I don't understand that.
You're not going to stop kids from smoking if they choose that path.
Sure. I mean, I do think you can, like, make things less attractive, you know? Like, don't tell kids that, like, smoking is healthy. Or don't flavor it so that it's, like, enjoyable. Like, cigarettes taste terrible. And...
Yeah. Again, I've got an older perspective than you. I mean, I come from a council estate, and everybody smoked cigarettes because that's all that was available.
Sure.
Let me be clear: no one ever thought it was healthy, but everybody smoked cigarettes.
It's like a social thing, you know. It's like, yeah, let's just like do some cancer together, you know.
But I mean, we're talking end of primary school as well, not as a teenager.
Yeah, I mean, these kids, like, here we go. There's a document on this, dude. Why did the vape industry in the United States turn to disposable? So I agree, like, convenience sake, it's terrible. Right, it was the flavored vape pod ban. Like, pods were not okay, but disposables apparently were. And apparently, like, they're still illegal, but the FDA just, like, doesn't really do much.
Yeah, don't even get me started on the FDA. Just the most fundamentally useless department in the US.
Yeah, we could argue all day. Who's in charge of it now? Mr. Bobby K? RFK? Isn't RFK in charge of it right now? I think he is, dude.
Probably.
Who's in charge of the FDA? Let's see.
I thought that was the whole point. I thought you couldn't have...
No, it's Martin Markey? Or Robert Califf? This guy doesn't look trustworthy.
Which branch is White House?
I guess this guy's apparently the head of the FDA. I have no clue who this guy is.
Legislative, executive, judiciary.
Okay. What branch of the government is the FDA? It is... Ooh. That's not really an answer. It's the executive branch.
Executive.
Yeah, this is weird. This is why Trump is able to just, like, fucking fire everybody in these things. I always thought that was weird, because I was like, wait a minute. Aren't these, like, appointed positions, but, like, within, like, Congress? And it's like, no, it's all... Why are these things part of the executive branch? Who came up with this? That was a bad idea. Why put, like, one crazy nut job in charge of, like, huge organizations that are supposed to be nonpartisan, right? Like, health should be a nonpartisan thing, we would hope.
This is the joke. Most US foods are banned throughout the world.
Yeah, because they have, like, toxic chemicals in them. Or, like, Red 40, right?
Yeah, I mean, things like unnatural dyes have been banned since before I was born.
Have you seen the one with the cereals? Like, when they look at cereal between, like, the US and the UK. This is so bad. So this is apparently, like, the US version of Frosted Flakes. And, like, they look at, like, the difference in the ingredients, right? Versus the UK version, Kellogg's Frosties. So you're right. Yeah, a lot of things are, like, kind of banned. So ours is, like, milled corn and sugar. Yours is maize and sugar, barley. Vitamins and minerals. Yeah, so, like, some of this stuff is just, like, not allowed, I guess. There's some crazy examples, because even, like, the UK isn't, like, too much, but, like, look at this, for instance. US versus Germany for Fruit Loops. Bro, what's all this shit on the left? What's going on here? What are they putting in my Fruit Loops? That's pretty funny. Yeah. I think a lot of it comes down to the dyes and the preservatives is what it is. Or even, okay, the big one I'm seeing here is like US versus UK oatmeal. Look at that. Look at that difference, dude. It's like here, rolled oats, sugar, freeze-dried raspberries, freeze-dried strawberries, natural flavoring. Awesome. Here it's like oats, sugar, creaming agent, flavored and colored fruit pieces, dehydrated apples, treated with sodium sulfite, artificial strawberry flavor, citric acid, red 40, salt, guar gum, niacinamide, vitamin A palmitate, reduced iron, peroxidine, hydrochloride, riboflavin, thiamine, mononitrate, folic acid. Why are all these?
Acid?
Why folic acid? Wait, what?
It's good for pregnancy.
Let's see. Why does the U.S. add folic acid? Oh, to help prevent neutral tube defects in newborns. Okay, I get it. So the government's like supposedly trying to help us, so they put all this stuff in the food. Is that what we're supposed to? We're supposed to trust the government? You think so?
Oh, I would imagine it's because too many people choose to have children at home in the US.
Yeah, one of my friends had delivered their baby in their bathtub twice, like 2 different babies. I was like, what? Excuse me. We have hospitals. We have hospitals.
But isn't that the joke? Doesn't it cost more to have a child in hospital in the US than it does to raise a child for 18 years?
Probably. I can't even think. I can't even think about those bills. That's something like you need a stable job in healthcare. None of which I have. I do have healthcare, but it's not the best. I don't think it's like pregnancy healthcare. It's okay. Sensation. I'm technically a British citizen, so I could go over to the UK, right? And as long as I'm there for 6 months, I think I apply for. I think I'm eligible for NHS, right?
Actually, I don't know how that applies to foreigners.
I'm technically a British citizen. I'm not a foreigner.
Well, yeah, so yeah, I don't know how. Yeah.
I think the only caveat here is that I have to go like marry a British girl as well. I don't think I can bring like my American wife and then have her get like British healthcare. I don't think that works like that. Anyways. Jeff says, have I asked you why applying work to a mass increases its speed differently depending on the mass initial speed? Yeah. That's the work energy theorem, Jeff. Work energy, which says that the net work applied to an object is equal to the change in the kinetic energy. So it's equal to the change in 1/2 mv squared. So in that case, net work is equal to 1/2 m, and then it's like v final squared minus v initial squared. Are you asking? Yeah. So, yeah, depending on what your initial speed is, will change what your delta. Well, I mean, the delta's the same, right? The delta's the same, no? Oh, intuitively, why is that? Law of diminishing returns. What's up, Femvox? Well, maybe let's think about it this way. So, work is equal to force times distance. Work is equal to mass times acceleration times distance. There's something here where I'm getting mv squared or something. Is this one of those kinetic friction things? Yeah, where we just like kind of wave our hand and just accept it. Maybe. want to see if this works out, actually. Sorry. So this is work. Speed is all relative. Yeah, it depends on your reference frame for sure. So this is m dv/dt. Oh, and actually, sorry, this is an integral. Sorry, my bad. Because things can vary with time. So work is equal to the integral of force times distance. So work is equal to the integral m, and we say like, and so this is like a dx. So work is equal to mass integral d squared x dt squared dx. Does that like help me out at all? I don't know. Oh, you get the math part? Well, I mean, from an intuitive point of view, when you do work on a system, you increase the energy of it, right? And the energy has to go somewhere. So if you're not putting more energy into the potential, then you have to be dumping energy into kinetic, right? Like the energy has to go somewhere. Energy can't be created nor destroyed. It can only be like transferred in like forms. So when you apply a force to something over a set distance, you are inserting energy into the system, and that energy has to go somewhere. Sometimes it can work to push something up, why is there less energy the faster the object is? This is where I think Fembox is correct with diminishing returns. It's not that there's not less energy. There's the same change in energy. But if you're already at a really high energy, that delta isn't very noticeable. Does that make sense? For instance, like think about like, let's say there's like a bank, okay? And in one's account there's Jeff Bezos. Here's his bank account, right? And then in another account, here is my bank account, you know? And let's say that I do some work. I do work, okay? For instance, let's say like I teach someone chemistry for 1 hour, right? Okay, and that generates, I don't know, like $100. Okay? That work I did is kind of like energy, and it has to go somewhere. Right? If I apply it to my bank account, that $100 looks great. That looks like a huge change in my account. But if I give it to Jeff Bezos, I mean, he just shits on that. So he doesn't really see much. The delta isn't negligible to him. Femvox says, as the object speeds up, a constant force will have to apply over a longer distance to give the same change in energy, so more work must be done for that energy change. Yeah. If you push something by a given amount, it should speed up by a given amount. Well, no, the energy changes by a certain amount. Right? But the energy is related to like v squared. I think I see what you're saying. Not yet. The velocity doesn't change. It's the energy is like the whole thing. It's like the whole account. Yeah, and I guess it comes down to the math here, right? Right? Because delta v squared is v final squared minus v initial squared. So I see what you're saying. So for instance, like 6 squared minus 5 squared is not the same as 5 squared minus 4 squared. right? This is 36 minus 25, which is, yeah, this is like 11, where this is equal to 9. So, I get it. I see what you're saying. Why does the velocity not go up by the same amount? Yeah, it's because it's squared, and it's... It really shouldn't matter how fast something is going. Let's see what Fembox was saying. Yeah, it doesn't matter for the change in the energy. The change in the energy is the same, Jeff. If you apply 1 joule of work, it's the same change in the energy, but in terms of like the change in the velocity, it's not. I think this is kind of like my explanation for it, right? Both accounts go up by $100, but if you wanted to talk about like how powerful our bank accounts are, there's not really there's not a measurable change on Jeff Bezos here. Like, my buying power doubles, but Jeff Bezos just goes up by like 0.001% or something. That's a cool question, though. I like it, Jeff. Make me think. It's gonna make me think. Okay, but I think I've done enough thinking today because we're at almost 2 hours. Physics should behave. No physics behavior. All right, cool. Let's close this stream. All right. Thank you, everyone, for coming to office hours. Really appreciate everyone's questions, everything. Our next stream will be tomorrow. That's an hour later, 5 p.m. Pacific, 6 p.m. Mountain for you, Jeff. 7 p.m. Central, 8 p.m. Eastern. Keep a lookout in the Discord. We are starting summer camp next week, and I have to announce all the rules and fun stuff. I wish physics was more intuitive. Sometimes it is, sometimes it isn't. You know, it varies. But yeah. Any other things? Yeah, please. If you found us through Twitch or YouTube, make sure to join the Discord, and then check out our calendar for everyone else who's running events. I think Zach is teaching tomorrow morning. Is that right? I think Zach is teaching. Where is it? Where's our calendar? Yeah, Zach is teaching. Tomorrow afternoon, actually, at noon. Okay, very cool. That's actually right when I'm doing my physics class. Okay, so if you want to go say hi to Zach tomorrow at noon. He's a little bit later than usual. Cool. All right, let's see. Let's go raid somebody. Who am I going to raid? Bonding time and art. Well, what's Sage doing? Is she back, or is she just chilling? Oh, she's not at her desk. Looks like, hey, speaking about physics, you want to do some more physics, Jeff? Go ask physics and depression about this. Go ask him the question about kinetic energy and stuff. He would love this. I feel like he's doing. This looks like. I think this is current. Yeah, let's go say hi to physics and depression. He's a fun guy. Okay. All right. Enjoy the rest of your Tuesday, guys. We will see you tomorrow. Peace.
Bye, everybody.